Good morning, dear students. Last class we were discussing about block diagram reduction techniques we were discussing, and we have done one numerical also. So next example we have to take up today. So in the next example, they have given a block diagram here. Okay. And what all we have to find? So we have to find open loop transfer function, feed forward transfer function, control ratio, feedback ratio, error ratio, closed loop transfer function, characteristic equation, and closed loop poles and zeros if k equals 10. Okay. So this is the given block diagram. What we have to do is we have to simplify this to canonical form. What is a canonical form? We will be having only one loop in the block diagram. You will be having one forward path, you will be having only one feedback path, and you will be having a summer. So that's what a standard canonical form which we have discussed in the last class. So we have to reduce the given block diagram to the standard canonical form. Let's do that. So standard canonical form, we will get it by simplifying the inner loop, correct? So this and this are in cascade. You can directly multiply these two blocks and you can have one single block, okay? So that's what we have done here. We have grouped this first and second block since they are in cascade. So that rule is allowed that we have discussed. So we have grouped and we got this block here. And you can see that here it is a loop, okay? It's a feedback loop and negative feedback loop, the sign indicates. So this we have to simplify. So we have seen the formula for simplification of that negative feedback loop system. So this is what the formula, that is forward path gain divided by 1 opposite sign. Since it is a negative feedback, we have to take plus here, the forward path gain into the feedback path gain. Okay, if this is the block, this is what the loop which we are supposed to simplify. This becomes my GFS, that is forward path gain. This becomes my feedback path gain, that is what we call it as H block. Okay, that we have done it by applying this formula. You can see here I have taken GFS here, which is K divided by S plus 1, and H is just S here. So in the denominator, I have 1 plus GFS is what? G is what? K divided by S plus 1, and H is what? It is simply S. So we have got this, value, and that, we have simplified and when we taken here. So we have replaced this entire negative feedback loop and we got one single block. So this is now our standard canonical form. So now this becomes my new G. This becomes my new H. Okay, so this is for the standard canonical form. So we don't simplify this further, because what we are supposed to find out, we have to find out few parameters here. For that, it is better to keep the block diagram in this standard canonical form. So this is G of S, this is H of S, this is R of S, and this is C of S. Okay. So now I have taken the same block diagram here in a small size, and we have taken all the different parameters which we are supposed to find out. So what is our open loop transfer function? It is B of S divided by E of S. Okay. So that is B of S divided by E of S, which is equal to G of S into H of S. Very simple. We have G of S here, we have H of S here. You have to simply multiply these two to get the open loop transfer function. What is a feed forward transfer function? So it is C of S divided by E of S. C is here and E is what here? That is output of the summer is what? E of S, which is nothing but G of S. That's what the equation says. So simply the G of S is what the feed forward transfer function. What is a control ratio? It is output by input, that is C of S divided by R of S, which is equal to G of S divided by 1 plus G of S into H of S. So this is G of S, this is H of S. You have to simply substitute. Similarly, feedback ratio is B of S divided by R of S, which is equal to G of S into H of S divided by 1 plus G of S into H of S. Direct substitution, you please do it and get the value. Error ratio, E of S by R of S, is equal to 1 divided by 1 plus G of S into H of S. Closed loop transfer function, is same as control ratio. Okay, you need not repeat the calculation. Closed loop transfer function is same as the control ratio. So characteristic equation is the denominator of the control ratio, we call it as. So 1 plus g of s into h of s is equal to 0. You have to substitute here for g of s and h of s, that's all. Okay, you will get the values. So whatever equation you get, okay, for the control ratio, take the control ratio c of s by r of s, or you can take a closed loop transfer function. So here you have to get a numerator polynomial and denominator polynomial, and you have to factorize that and identify how many poles and zeros you have. You will get it, and you have to substitute k value 10. That's what given here. Substitute k value 10, and you have to do what? The numerator polynomial what you get and denominator polynomial what you get, you have to factorize. So denominator will give you the poles, and numerator will give you the number of zeros. Okay, so very simple, you can do it, I feel. So next example. So here also, one block diagram is given. You have to find out same parameters, that is open loop transfer function, feed forward transfer function, control ratio, feedback ratio, error ratio, closed loop transfer function, characteristic equation, closed loop poles and zeros if k is equal to 100. Okay, look into the block diagram here. So what actually happening here? We have one takeoff point, and the takeoff point is further branching. Okay, so you can split this into two takeoff point. Okay, then you get one single loop here, one single loop you can have it, that you can simplify. And these two blocks you can see here, they are in series, you can simplify. We'll see how to do that. Okay, so this is an exercise, you please do it. I'll give you the hint. So you have to group these two blocks which are in cascade, correct? These two are in cascade, and this takeoff point you split into two. You take a separate path for this summer, take a separate path for this summer. Okay, so these two you group it according to cascade. These two you have to group it according to cascade rule, and this inner loop you have to simplify. Correct. Then takeoff point you have to move ahead of this block. Moving a takeoff point ahead of a block or after the block, we call it as, that technique we have already discussed. So that you have to do it. Then you get a canonical form. Once you get the canonical form, it is as simple as the previous one which we have discussed. Once you get the canonical form, you have formulas for all the parameters. You have to simply substitute the values to get the answer. Okay, so I repeat here the reduction technique which you have to follow to reduce the given block diagram into canonical form. First step is group these two blocks and group these two blocks according to the cascade technique. Take a separate takeoff point here. This takeoff point separately you have to take for this summer, and one more takeoff point you have to take separately to this summer. Then simplify the inner loop, inner feedback loop. You have to simplify. What is the formula for that? We have seen that it is G divided by 1 minus G into H. G is the forward path gain and H is the feedback path gain. So that we have already discussed. You have to simplify that and move the takeoff point ahead of the block, and then you have to simplify, or you get a canonical form, and there you identify G and identify H and substitute the formulas which we have given for all these parameters, and you get the values. Okay, next example. So we have a block diagram, and here you have to simplify this to one single block. Okay, so we have to simplify this given block into one single block, and we have to follow the so reduction technique which we have discussed previously. Okay, so what here we are trying to do? So there are so many ways of reducing this. You can move this takeoff point ahead of this block. I repeat, you can take this takeoff point ahead in front of G3, you can take it. Okay, then you can simplify, that also possible, or else you can shift this somewhere to the left. You can shift this somewhere to the left and you can just simplify. Okay, so that's what here we have done. We have shifted the somewhere to the left. Okay, shifting somewhere to the left, you will see that it was here, summer was here before, now it has gone to the left of the G1 block. I repeat, it was after the G1 block. After the G1 block summer was, now we have taken summer to the left of G. So for this particular signal, which was early entering here, now is entering here. So this particular path unnecessarily experienced the gain G1, which we have to avoid. So what we have done, this particular line has been multiplied by 1 by G1, so that this block, whatever gain contributes, that get cancelled, so that you will be back to your original state. Okay, so it is a valid movement what we have done, and we have shifted a summer to the left of the block G1. So now just G1, G2 are in cascade. You can see here G1, G2 are in cascade. You can group them and you can multiply the the functionalities G1, G2 to get one single block. Okay, that's what we have done here. Okay, next is again interchange of summer we have done. So I have summer 1 here, I have summer 2. I can just interchange. See, this input I can feed here, and this input I can take it to the summer. It is valid. So input swap we call it as. If there are two summer next to each other or they are in cascade, you can swap the input. Okay, so you are adding A to B and then you will be adding to C. It is same by it is same as adding C to A, then adding B to the sum. It is same. Okay, so what you are doing is, say some A and B is adding here, signal A and signal B is getting added up, you are getting C, right? And you are adding that D here. So you can swap these two inputs here, you will get the output same. So what I do is interchange of summer is possible. In other words, I swap the inputs which I am feeding to the summer. Okay, you can do that. So we have done it. So what we have done, that input which was coming here, I took it here with the same polarity, and the input which was coming here, I took it here. Okay, so this is what a loop I have now, a loop, okay, with a forward sign. So we have to simplify. This is a forward path, this is a feedback path, positive feedback we have here. And how to simplify? Forward path gain divided by 1 minus, because I have plus here, so I'll get in the formula minus. So 1 minus the forward path and the feedback path gain. Okay, so now I have simplified. That is forward path G1, G2 divided by 1 minus forward path G1, G2 into the feedback H1. Okay, so now you have one more loop here. You can see one more loop, correct? So summer and a block here, a block here, and here is a feedback path with a negative sign. That is negative feedback I have. So same rule we apply here. These two blocks, they are in cascade. Just multiply these two. Okay, and apply the loop simplification formula. That is G divided by 1 plus here. Why plus? Because I have minus sign here. So I'll be having 1 plus forward path into feedback path. Okay, so first let us group these two blocks. We have done it. Then we have simplified that single loop according to the formula, that is forward path divided by 1 plus, and that simplification we have done. So we got this particular block. Okay, so this is what we have, a standard canonical form. This you can further simplify to one single block, or else this itself is the last step we can call it as, so that we can calculate the different parameters like control ratio. We can calculate error ratio and forward block gain, reverse block gain, all those parameters. It's easy for calculation if you keep the block diagram in a canonical form. So this is what the final reduced block diagram we have. Further, you can reduce this for C by R estimation, or else we can keep this as the final reduced block. So next problem we have. So we have to find the transfer function for the following block diagram. We have to calculate the transfer function of this particular block. Okay, so you can see here, this takeoff point is disturbing to group these two, correct? Okay, so you can take this takeoff point to the left Okay, take this takeoff point to the left. Then what you will get, G2, G3 you will find in cascade, and you will be having this one forward path, and you will find this, that is G4 path, as another forward path. Why do I call these two as forward path? Because you can see here, originate from the same point, ends at the same point, especially summer here we have, they're meeting in the summer. So I call these two as a forward path, two forward path. So parallel line simplification we have discussed, we have to simply add two path gains. We have to simply add two path gain. Okay, we will see how to do it. So first is, as I said, you have to shift this takeoff point from point A to point B. You have to move. I repeat, from point A to point B, you have to move the takeoff point. Then you can see that G2, G3 will be in cascade. Correct? So let's do that. So we have to shift, you have to shift this takeoff point. So while shifting the takeoff point to the B, what actually happens? This particular path will suffer. How it is suffer? If you take a signal here, you would have got G2, correct? You have got G2 if you take a deviation at this point. But if you are taking a deviation here itself, you will be missing the effect of G2 that I have taken here exclusively for that feedback path. So for the feedback path, I have taken that block which we will be missing by moving from point A to point B. We missed this block. We have taken that separately here so that my feedback signal is unaltered now. It's unaltered now. By moving from point A to point B, the signal strength is unaltered because whatever the gain we are missing by moving from point A to point B, that we have compensated here, taking a G2 block in the feedback path. Okay, it's a valid simplification. We have moved the takeoff point from ahead of G2 to, that is in front of G2, we are moving to the back of G2 now, and the loss we have compensated. Okay, so next what you can see is, once you move from point A to point B, you will see G2 and G3 in cascade. Okay, you have to group those two blocks, and you can see that from here to here it is one forward path, and from here to here it is another forward path. That is two parallel lines. Two parallel lines, you can simply add them. So G2, G3 can be added to G4 because this line and this line are in parallel. Okay, that's what here we have shown. G4 plus G2, G3 is the block I will be getting by simplifying this purple circle, purple ellipse we have taken here. You can simplify that and you get G4 plus G2, G3. I repeat, how can I write G4 plus G2, G3? So G2, G3 found to be in cascade because point A has been shifted to point B now. Correct. This takeoff point we have shifted to B. So these two are in cascade, and this line are parallel to each other and meeting at a summer. You can simplify that by adding these two blocks gain. We have done it. Okay. So that's what we have seen in the last slide. So that's what you can see here. It is grouped now. Okay, I repeat, G2, G3 has been grouped, and G2, G3 is in parallel with G4. We will be simplifying. Okay, you get this particular block. Okay, so now these two were in cascade. We have grouped that. Okay, now how to proceed with the simplification. So this takeoff point has to be moved ahead of this block. Okay, this takeoff point B, now I have to move in front of G4 plus G2, G3 block, then only I can simplify, otherwise no. So let us do that. So I have to move the point B, you can say behind or ahead, behind or ahead, you can use it. So I am just moving this point B here. Okay, ahead of the block I call it as. So you can move, you have to move it. So how to move? You can move that block, that is point B here, point B which was here, I am moving to the point C. You can move that. If you move, then what is actually happening? So from here to here, if you take a move, you will find this block unnecessarily contributing to this feedback path. This feedback path unnecessarily get the effect of this block if I move from here to here. From point B to point C, if I move, I will get G4 plus G2, G3 gain will be affecting the feedback path, which is not required. So what we do is we take the reciprocal of this block and I will have it here, so that by moving from point B to point C, whatever the effect, unnecessary effect getting will get added up, that we can cancel. Okay, so that's what we are doing. So from from point B to point C we will move, and this block unnecessarily getting getting what we call contributing to the signal, that I'm canceling here. Okay, so this block effect I am canceling by taking reciprocal of the same in the feedback path. Okay, so now what you can do is you can simplify this now very easily. Correct, I have one summer, I have one forward block, and I have one feedback path with a block gain of H2. So this is a loop, negative feedback loop fashion we have. So we have a standard formula for this, that is, if I take this forward path gain as G, if I take feedback path gain as H, so we can simplify this purple ellipse into one single block, that is G divided by 1 plus G into H. That one standard formula which we have learned it, we can use that, and you can simplify. So this is what the loop we have to simplify, and which were in cascade we have taken it. And this is what in the last slide we have marked to simplify. So we have to simplify that, and I'll get one single block now. So this and this are in cascade. You can multiply these two blocks, and you will be having again one inner loop will be formed, that is negative feedback loop, because minus sign I have, that you have to simplify. Okay, so you will get this one single block after simplification. This is the standard canonical form. Since the transfer function has been asked, this has to be further simplified. So how to simplify? This is what we call it as now the new forward path gain G, and feedback path gain is 1, unity feedback. Then what is the formula? It is forward block gain divided by 1, opposite sign of this, that is plus 1 plus forward block gain into 1. So after simplification, I'll be getting this particular transfer function. You please try out at home. Next question. So again, here we have to find the transfer function for the given block diagram. So very interesting here, because we have two summer in series. The pattern looks so different, which we have not seen in the previous problems. Okay, we will see how to do it. So simple simplification, let us do it first. So simple simplification is one loop which is very clearly visible here. This takeoff point 1 you split into 2, that is separately take a line for this, and one separate line you take for this particular path H3. Okay, so you can do that, and you get a more clear block diagram. I have done it. I have just split the point, take a point into 2. Separately I have taken a path here, and separately I have taken a path for this particular path. Okay, so this looks very simple. It is a loop fashion, you can simplify. Okay, it is a loop, feedback loop, you have to simplify. So we have done that. That is forward path gain divided by 1 plus forward path gain into feedback path gain. We have done it. We got this particular block. Now you have to shift this takeoff point next to this block. Okay, from point A to point B you have to move the takeoff point. Okay, so you can do that. Okay, by doing that, what you have to do, so if you, instead of taking a branch here, if you are taking a branch from B, you will find that this block will get this block gain will be contributed to this feedback signal, that you have to cancel. So you have to take a reciprocal of this block in this particular path if you are taking a branch at a point B instead of at a point A. So let us do that. We have done that. Takeoff point from A to move, we have already moved. We are taking a branch from point B now. So I have to take a reciprocal of this block. I have to take a reciprocal of this block now here, okay, so that it get cancelled. So instead of here, we have taken a branch here. The effect of this block, we are nullifying by taking in the feedback path in a reciprocal fashion. So these two are in cascade, these two are in cascade, you can simplify, okay. So, this you can see two parallel path, correct? This is one path and this is another path meeting a summer. I repeat, this is not a loop. Look into the direction, please. Though it looks like a loop, it is not a loop. So here you can see one forward path meeting a summer, and this is another forward path, or what we call another parallel path meeting the summer. So this and this are two, I should not use forward path. It is two parallel lines. This is the origin, that is point B is the origin. This is one in one line, and this is the another parallel line. So these two are two parallel line meeting the summer. So you have to add these two paths. Okay, you have to add these two paths. So we have done here, correct? H3, that is one line signal. Okay, that is one line signal strength H3 plus this and this we have to multiply because they are in cascade. We have done it. So this is another block. We have to finally take the addition of these two because they are in parallel. Okay. So that is what the next simplification. Once you do that, you will see that one single loop existing, because this complete purple ellipse will become one single block. That's what the block that's what we have shown in this green patch, and these two are in series. You can you can simplify. So you get a final block diagram like this. Okay. Again, this is a canonical form, standard canonical form. How to simplify standard canonical form, you already know. It is forward block gain divided by 1 plus forward block gain into the feedback block gain. Okay, feedback path gain. Okay, so and after simplifying the terms, you will be getting this. Just please try at home a very simple simplification. Okay, next. So we have a transfer function here. So, sorry, we have a block diagram for which we have to find the transfer function. Okay, this is also a little complicated because you have so many summer here in the second line. If you take this as a first line, you have a summer in the second line. You have to simplify this. Okay, so just look at the block diagram by shifting this takeoff point, which will help us in moving ahead. Correct, we can move ahead by just shifting this takeoff point. I call this takeoff point as A, and I'll try to shift this next to the G4. That is, after G4 I'm planning to take that point A. So I have identified this point A and I have identified this point as B. From A to B I have to move. Okay, so but while moving from point A to point B, what actually happens? G4 unnecessarily get added up. I have to cancel that to this path as well as to this path. There are two paths here. Okay, so for both the lines I have to do the adjustment. So I'll take a reciprocal of G4 to this path as well as to this path. That is two paths what we have. For both the path we have to take the compensation block which we have taken it. Okay, so the two lines I have shifted from point A to point B. So for both the lines I have taken reciprocal of this block so as to cancel the effect which is getting added or getting multiplied when I move from point A to point B. Okay, next, if I move, I have already moved. So you can see here one loop. This is a loop. How can I say? Look into the direction. It is in the forward direction. This is in the reverse direction. So this is what we call it as the feedback loop we have here. Negative feedback because I have a minus sign here. Okay. So you have to simplify this. It is a loop, negative feedback loop. You have to simplify. Okay. So okay, they have just grouped it, the cascade we are trying to group it. So cascade blocks has been simplified. Next, this purple ellipse will be simplified. You will be getting a block like this. Okay, that loop has been simplified and you will get a block here. Okay, and this is what the one more inner loop we have that you have to simplify. Once you simplify this inner loop should get multiplied with a block G1. Okay, so that is what the next step, you have to do it. And again here you have one loop. This is not a loop, you can see here, very sorry. This is a one forward path, this is another forward path. So these two are forward path here. So one is in the plus, another one is minus. So this is plus and this is minus, you have to subtract these two blocks. Okay, whereas here it is a loop. Just come up here, it is a loop. So this loop you have to simplify, negative loop you have to simplify, and these two are in parallel. So this and this you have to you have to take the difference of these two. So you will get section 3 simplified. You will find that this section 3, I have named this as section 3, that has been simplified as difference of these two I have computed. Why did I computed the difference? Because you can see here one signal entering to the summer, from the same point another signal is entering to the summer with a minus sign. So they are parallel path. Since the sign are different, I am computing the difference. So the difference you have to compute. Whereas this is a standard loop, negative feedback loop, standard loop, and that you have to simplify. Okay. So that's what the section 2 simplified here, section 3 simplified here. Okay, and you will get the after substitution you will get this, and this is the standard canonical form, and this you have to simplify to get the transfer function. Okay, so transfer function is computed already. Okay, so next problem. Okay, next problem, again we have to find the transfer function here for the given block diagram. Okay, so how to proceed with this? So here you have to shift again the takeoff point. Okay, takeoff point we have to shift, otherwise we can't proceed from point A to point B. If you move a takeoff point, from point A to point B, you can simplify. You can simplify. Okay, let us do that. Okay, so shifting the takeoff point from point A to point B, as I said. So I'm moving takeoff point from point A to point B. So if you're moving a takeoff point from point A to point B, this G3 has to be compensated in the feedback path. So how? By taking reciprocal of that, I'm going to cancel G3, which is getting multiplied while moving from point A to point B. So that is one simplification you have to do it. And you can see here, the same signal is going here and the same signal is going here. You have to separate the path. Okay, so you have to separate the path here. Okay, so how I can do it? So I don't take here continuously. I'll take this separate path for this, and again I'll take a separate path for this. Okay, you can do that. So what is the meaning here? Whatever signal is coming get multiplied by these two blocks and moving to this summer as well as moving to this summer, correct? So I can take it separately. I'll just go here separately and I'll take again the same set of signal and I'll be going here separately. I can do that. Just I'm duplicating this path because they have joined here. I just wanted to separate the joint. So I'm taking the signal here. So signal separation, I have done it here. Okay. So now these two are in cascade, you can group. These two are in cascade, you can group. And this and this are two parallel paths, you have to simplify that. And finally, you will get one single loop that you have to simplify. Okay, so I'll talk, I'll be calling this as a purple square, as first section, which we have to simplify. Okay, take that section. I have taken that section separately here. Okay, you can see that these two can be simplified. These two can be merged. That is, I can group because of the cascading pattern. Again, these two can be grouped, correct? So first we'll do that grouping, and then while after grouping this particular line and this particular line are in parallel. I repeat, this H2 block and this H1 by G3 block. This, if I group, I'll be having H1 by G3, correct? This H1 by G3 block, these two lines are in parallel, okay, with the same negative sign. So I'm keeping that negative sign same, and I have just added these two block. I have added. So it is like doing minus A minus B. It is minus A plus B. I have done it. So I got this, the block, and this is a single negative feedback loop. You have to simplify. Okay. So after simplification, I'll be substituting in its position. After simplifying this, I have substituted in the original block diagram, and this is how a new block diagram looked like. So again, G1 and this block are in cascade. You have to simplify, and you will get one loop here that you have to simplify. Okay. So I'll take this as section 2. Section 2, you have to simplify. Very simple. It is a loop fashion. You can simplify that we have taken here, and you have finally one loop existing, which you have to simplify. Okay. So it is not a loop. It's not a loop. Very sorry. This is a forward block. I missed the direction. Very sorry. This is a forward block, and this is the again a forward block, forward path I have meeting at the summer. So these two are in parallel. We have to add. So we have done it here. Finally, this is what the transfer function we have. Okay. So I'll just stop at this stage. I'll continue with this in the next class. Okay. This is multiple input and multiple output system. We will take up in the next class. Okay. Thank you.